Hello and welcome. Today we're going to investigate pressure in liquids. So we're specifically going to look at pressure in liquids with an open container, but let's just revise a bit. Pressure means to press. So pressure, we said, is the force, okay, divided by the area, and the unit is Pascal, and we said that 1 Pascal is 1 Newton per meter squared. So here we have a little simulation, FET simulations, under pressure is the name, and we're going to see a few things here. So we have a pressure meter, okay, and we're going to see a few things that affects pressure. So what we're going to do is we fill this up with water, so the density of this case is water. We can make it more dense and less dense, and we'll see the effect. And we go and we measure the pressure. The first thing that we notice is, what is the pressure outside of the water? Okay, we call this air pressure, and we're going to get to that in the next section. But we can see that the closer we get to the ground, the bigger the air pressure, and just before the water it's 101. Now we go into the water and we see that the pressure increases with the depth. So that's the first observation. Pressure increases with depth. So now I move around, and everywhere at the same level is the same pressure. So at 2 meters it's around 120, and if I can keep that needle around at the bottom, it's around 120. At 1 meter it is 111, 110, and we can see that the pressure is the same throughout. So the pressure increases with depth, and the pressure is equal in all directions in the same level. So although if I have a object, let's say an object is floating in the water over here, okay, let's rather do this. Here's an object floating in the water, and we have now the pressure pushing upwards, okay. The pressure pushing upwards on this object will also be equivalent to what the pressure would be. So it's not just pressure downwards, it's pressure in all directions on that level is the same. So the pressure in all directions, whether it is up, whether it is to the right, to the left, or downwards, everything on that specific level, okay, on that level, on that line, we have the same pressure in all directions. The next thing that we're going to play around with is the density. So if let's say I put it way at the bottom, that's 3 meters underneath the surface, and I exchange my water with gasoline, a quantity that's less dense, I can see that my pressure reduces. Okay, and if I put it with a container with 3 meters of honey above it, I increase my pressure. Okay, still the same atmospheric pressure, but the pressure increases as the density of the liquid increases. Now, why is that? We know that pressure is the force over the area. Now, at 3 meters depth, we've got the weight of the honey. So the weight, okay, divided by the area is going to give me the pressure, okay? And the more the liquid weighs, the bigger the force, which increases the pressure. So therefore, the weight affects the pressure. The height also affects the pressure, because the weight depends on how deep I am. Okay, so the height under, or how deep I am under the water, determines how much water is above me or how much honey is above me, which influences the weight. And last but not least, what happens if we take this calculation to another planet? Okay, so firstly, we will see that this assumes that there is air pressure on the planet Mars. Okay, so that's not true, but what we see is we have the moment the gravitational acceleration increases, the pressure also increases. So there is an effect that gravity also has on that. And once again, why is that so? Because the weight is the force or the mass times the gravitational acceleration. So the force or the depth, the density, and the gravitational acceleration all influence the weight of the water above the object, which increases the pressure. Now in this simulation here, we can now see that as I move the hole down, okay, we're going to investigate how far the water squirts. Now, the further the water squirts, we see the distance from the container, the more the pressure is. Okay, so if we take it down, we see that the distance from the container increases, and that means that pressure increases with depth, as we've seen. And the reason for that is because there's more weight above. So the hole has the same area, but there is more weight of water above the area. So the force over the area is bigger, which increases the pressure. The last thing that we want to see is what happens when I change the shape of the container. Okay, so here we might now think that because, let's just turn this back to water, okay, and let's just take it back to earth. Okay, so here we've got a few things. So the moment we think of pressure increasing with depth and the amount of weight above this, we would think that here on the right hand side there's obviously more water above, so the pressure on the right hand side is going to be way more than the pressure on the left hand side. So let's just investigate this. The pressure on this side at the bottom is 130, okay, and on this side it's also 130, and even here at the point where there's almost no water above it, it's also 130. And that tells us that the pressure does not depend on the shape. So let's quickly go to the other one, and we see that at the bottom it's still 130. Irrespective of the shape of the container, the pressure would stay exactly the same. So in this simulation, they ask us to calculate the pressure of a leaking tank. So the company wants to decide how to build their water tanks and where would the leak be the most pressure. So if we take it down to 0, okay, at the bottom of this tank the pressure is 4.76. At the bottom of that point 4.76, and the bottom of this tank we would have 4.76, well, yeah, over there. So what we see here is that pressure does not depend on the shape of the container, because it just depends on the amount of water that a pressure pushing downwards. So the fact that pressure is the same at every single depth is the reason why we don't have a effect of the shape of the container. So the 4 things that we've learned so far is pressure in an open container is acts in all the directions, okay, up, down, left, right at the same depth. The pressure increases the deeper you go. The pressure depends on the density. The denser the liquid, the more the pressure would be, and that the pressure does not depend on the shape of the container. So now we're going to play around and find a new equation for density at a certain depth. So we know that density is force over area, and we've said that that force can be the weight, the pressure. So pressure is force over area, and we know that the density, okay, is mass over volume. Okay, now the mass can be called the weight. So if we say mass is density times the volume, how do we turn mass into weight? We times gravity. So the weight then, if I times gravity on both sides, I get density times the volume times gravity. Okay, and we know that volume is height times area, so the weight is the density, the area, the height, and gravity. Okay, so mass is density times volume, which is area times height. If I want to change mass into weight, I times it with gravity. So if I times mass times gravity on this side, I do it on that side. Same thing happens on both sides. So here we have m, and we're timesing g. So just to show you where the g comes from, okay, we times with gravity on both sides. So mass times gravity becomes weight, and then we have this. And we know that volume is area times height. So if the force is weight, which we said in the water, that comes down to the fact that pressure is density, area, height, gravity over area, and your mathematics will tell you that that cancels. So that pressure in a liquid depends on the density, the height, and the gravitational acceleration. This is how we can calculate the pressure at any given depth. So the depth is the height, or the height is the depth of water above it. The density is the density of the liquid, and g is the gravity, the gravitational acceleration on the planet, which just depends on which planet you're doing it. Usually we'll be using 10 in IGCSE physics and 9.81 in AS physics when we're on Earth. So if we do this on Earth, which we will be doing most of our 99.9% of our calculations will be on Earth, this would always be equal to the Earth's gravitational acceleration.